Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you again in third week lecture series. In fact, I have started in the second week permeability and seepage topic, but it has not been completed yet. Partly I had to take up, and today remaining portion of the permeability and seepage I will complete first, and then I will move to compaction. So, permeability, various aspects of permeability we have discussed, and how to determine the coefficient of permeability for different cases, how to determine equivalent permeability, how to determine in the field, how to determine in the laboratory, all we have discussed. Now, when flow is taking place through the soil, actually we have to know what law is following, what path it is going, and already we have discussed that the flow taking place and where flow is taking place, this Darcy's law is applicable, and Darcy's law gives you that velocity is proportional to hydraulic gradient. That means, when there is a head difference, that will cause the flow. Now, when there is a flow is taking place over the length, then there will be head may not be same throughout, because at upstream there is something head and downstream side is something else, and it will be continuously there will be head loss. So, sometime we need to find out what is the head at any point. So, for that we have to find out what is the governing equation, and then we may have to look for solution. So, for that we are trying to develop that equation today, that is equation of flow through soil, and for that we are taking one element here, and this is the element, and which is having dimension dx, dy and dz, and it is at a depth from the ground, it is h, and we can imagine that flow is taking place from all three direction. Flow is in this direction, flow from this direction, and flow from this direction, and in that case we will try to mathematically we will see this, and finally we will arrive at the equation. And this is the flow. When this flow is taking place, suppose in x direction, the component of hydraulic gradient I x, we can say the hydraulic gradient 3 different I x, I y and I z at the center of the element. That means, if element I have taken something like this, and this is the midpoint, and I can, if I this is the dx length. So, this side dx by 2, this side dx by 2. So, we are applying the equation at the midpoint, and in that case I x mathematically is derivative of h with respect to x, and it is negative sign, because head loss is there in the direction of flow. The rate of change of hydraulic gradient, that is del I x del x, that is how it is changing, that is I have mentioned that flow head loss will be there continuously. So, rate of change, that is you once again you can differentiate this I x. So, that will be the thing, and then if I do that, then I will get this expression, and this del 2 del x, and hence the gradient at the face of the element nearest to the origin, that means before, that means before the midpoint and after the midpoint. I consider the nearest is the before the midpoint, then it will be original was is this and this is the change. There is a bracket mark missing. So, otherwise this is the one del I x del x into minus dx by 2, because over that much distance, the negative direction. So, ultimately if I simplify, you will get this. Now, similarly I can find out from the Darcy's law, q equal to a k I, and a is nothing but when the flow is taking place in the x direction, flow will be a cross section in y and z. So, that is why dy and dz is the area, k is there, and this is the I. So, we have got the then this is the flow, and similarly the gradient at the farthest from the origin, that can be again similarly this can be obtained minus del h del x plus this. So, it will be this expression, and therefore, the flow will be this is the I, and then correspondingly similar to this for flow, this is the expression. So, we have got question equation 1 and equation 2, one is the flow in nearest and one is the farthest. That means, this represents nothing but flow in and flow out. The expression 1 and 2 represents respectively the flow into and out of the element in the x direction. So, net rate of increase of water within the element, that is nothing but the net rate of change of volume of the element, and that is 1 minus 2. And if I do the previous equation 1 and equation 2, I will get this expression. So, k x del 2 h del x square dx dy dz, this is the volume, actually volume of the element, and this is k x into del 2 h del x square, additionally we are getting this is the change of volume in the x direction or net flow. The way we have done for x direction, we can do also similarly for y and z direction, and if I add all three, then similar expression we obtain for y z direction, and the sum of the rates of change of volume in three direction gives the rate of change of the total volume. So, I have got x direction, similar procedure, following similar procedure I can for y direction, I can get for z direction, all three can be added, and that will be giving you total change of volume. And so, that if I add this, so everywhere dx dy dz will be there. So, it will be taken out, and this initial part, this one for x direction, this one for y direction, this one for z direction. So, that means, this will be the total equation for change of volume. Now, we know that under laminar flow condition that apply in seepage problem, there is no change in volume, and the above equation must equal to 0. So, that since there is no change in volume, so total x, y, z, whatever total quantity we have got, that can be equated to 0. So, if I do that, then I am getting this is the equation. Equation 3 is the general expression for the 3-dimensional flow. If the soil is isotropic, that means k x equal to k y equal to k z equal to k, that means all three direction like k x, k y and k z, and this can be all can be written as k, that means all direction coefficient of permeability is same, then this can be taken as k, and if I put k everywhere, then k cannot be 0. So, ultimately the other expression will be, if k will be taken out, and after taking out either k can be 0 or remaining portion will be 0. Since k cannot be 0, so remaining portion has to be 0. You can see based on that I can get this equation. That means, this is the final expression I am getting, del 2 h del x square plus del 2 h del I square plus del 2 h del z square equal to 0. This is the expression I am getting when it is isotropic condition, And in mini seepage problem, we sometimes instead of handling 3 dimension, we handle 2 dimension, 1 dimension we can take 0, and then this expression will be reducing to, if it is generalized form 2 dimension, this is the equation, and if it is isotropic condition 2 dimension, this is the equation. And so, an isotropic, we are using the term isotropic again and again. The isotropic means what? The soil whose material properties are the same in all direction. So, this is the equation. Now, either solving this equation or solving this equation, or even if I can make it further simplified, I can make del 2 h del x square equal to 0, that is, it is 1 dimensional. So, this type of equation, either this or this or this can be solved actually mathematically, and then applying various boundary condition, we can find out the, if I integrate this one twice, then we will get 2 constants, and those 2 constants can be obtained by applying boundary conditions. So, there is a procedure for solving this problem. For many geotechnical problem, we solve this equation. Earlier used to do some ways, nowadays because of the availability of computer application, we can program it and do it. Perhaps we will not be able to go in details about the solution of this, but what we do actually in practice, I will try to discuss about that. So, now that was the equation, that is Laplace equation we have got, and that typical Laplace equation derived and expressed in terms of 2 conjugate function. There will be that equation also can be expressed in 2 conjugate function, one is phi and another is psi. Phi actually potential function and flow function, and this ultimately these 2 function is in such a way we can prove that these 2 function again they actually meet each other at right angle. That can be also proved, but we are not going to that. The only thing is that this phi and psi follow Laplace equation, that can be shown. So, you can see, we can assume that del phi del x equal to V x, and which is equal to k I x as per Darcy's equation. So, this is the one, and that will be again minus k del h del x, suppose in a x direction. Similarly, del psi del z equal to V z, and as per Darcy's law this one. So, these two we are getting del phi del x equal to this and del psi del z equal to this. Now, if you differentiate once again this one and differentiate once again this one. So, del square del 2 phi del x square if I do, then I will get k del 2 h del x square, and if I differentiate once again here del 2 phi del z square, I will get minus k del 2 h del z square. And now, this del 2 phi del x square and del 2 phi del z square if I do, then I will see because of this is minus sign and this plus sign. So, this will get cancelled, and finally, I think there is a mistake, this will be there, this may not be minus sign. So, these two together finally summation will be 0. That means, the phi function the way we have selected, that also follow Laplace equation. Now, similarly, the psi function also we can take psi del psi del z equal to V x, which will be equal to minus k again from Darcy's law equal to this, and minus del psi del x equal to V z, and that will be again minus del h by del z. Now, this one again if I now if I compare with phi function, and then we can see that del phi del x equal to del psi del z and del phi del z equal to minus del psi del x. Now, if I do del 2 psi del x square, this one if I differentiate once again. So, I will get this one, and if I differentiate this one twice once again, then I will get this one. So, these two again, this and this if I now add, then finally, I will get this expression, that means, it is equal to this is also Laplace equation. That means, the function we have taken phi and psi, they also follow Laplace equation. And this Laplace equation is called this phi and psi function. One is a potential function and one other is flow function, and this can be shown later on that they are function is such that when they meet at right angles to each other. Now, in the permeability and seepage issue, then finally what you have to do, we have to most likely most of the time we have to estimate the seepage flow quantity, and for that actually whatever equation we have derived, that can be solved and mathematically can be all obtained, but generally it is a complex one. So, because of that, conventionally in geotechnical engineering we use one graphical method. Very quickly we can do it without going through the details mathematics. Of course, mathematics will be there in the background, because whatever condition it satisfies, that graphical also conditioning satisfying those condition only you have to do it. So, for that actually we generally use a flow net, and in the flow net actually is a flow net is the combination of lines, and one set of line is flow line, another set of lines are called equipotential line. So, now what is flow line? Flow line is a line where the path which water particles follow in the course of seepage are known as flow lines. That water flows from points of high to low head, that always water will flow from higher elevation to lower elevation and lower head, and make smooth curves when changing direction. Hence, one can draw a series of smooth curves representing the paths followed by moving water particles. We can upstream side, we can consider at a point, at that point suppose we along with water moving, then tracing that point I can draw a line, smooth line, that will be equipotential. Like that number of them I can think at different location, and I can draw number of flow line. Similar to that, equipotential line, as the water moves along the flow line, it experiences a continuous loss of head. That means, when we are starting from at a higher head, but when water is moving in this direction, and whatever head was here, same head will not be here. So, there will be, because of this process of this flow, there will be loss of head will be there. So, that means, different below the water body or earth retaining structure below which water is flowing, if I can draw the head or potential at different points, and finally, if I join the points of equal potential, then I will get the equipotential line. So, definition of equipotential line is the line joining the points of equal potential. So, that is what, as the water moves along the flow line, it experiences a continuous loss of head. If we can obtain the head causing flow at points along a flow line by points of equal potential, joining the points of equal potential, one can obtain the second set of line known as equipotential line. So, these two flow line and equipotential line one can get, and that is the definition of flow line and equipotential. Now, flow nets, as I have already mentioned, that it is a number of equipotential line and flow line, combining them, drawing, when we draw in a particular pattern or following a particular law, that is actually flow net. The flow of water through soil can be represented graphically by a flow net, a form of curvilinear net made up of flow lines intersected by a set of equipotential lines. So, that means, this is the flow line, that is, it will be a curvilinear net made up of flow lines and intersected by set of equipotential line. So, there will be equipotential line and there will be flow line, and they will intersect, then there will be mesh like things will be prepared, that is called flow net, and that flow net can be utilized for calculating the amount of seepage through the body. So, this is a example, not example really, we can draw, we have drawn the flow net here following particular procedure. This is the suppose structure, dam structure, and water head is h, and here actually head is 0, head is here h and here head is 0. So, under this situation actually along this length actually head will be constant. So, this is the equipotential line. Similarly, here also head is constant. So, that is also equipotential line, and then this is one flow line, and water can also flow along this. So, this will be another flow line, and flow line, and I can imagine this is, since it is equipotential line. So, I can imagine one point when it moves from this side to this side, it will move like this, not exactly this way straight. So, it will move, go in a curved way, and it will go move this way. If a water point from here moves from this side to this side, it will move from here to here, this like this way. Similar point from here moves this side to this side, it will move this way. And now, I can imagine a number of equipotential. So, here is total head here, and head is 0. That means, head h is lost when it from moves from here to here. So, here it is h will be h itself, and this one it will be slowly reducing at different points. So, I can make it equidistant. I can make it, sorry, this is the end of flow line. So, this is the flow line. So, I can along this it is constant. So, this is the from loss from here to here, loss from here to here, loss to here to here, it will be equal. That accordingly I can plan, and then it is a not a very simple to draw this one. Only one thing one has to remember, that this is the flow line, this is a flow line, this is a flow line, this is a flow line, there is a flow line here, and there is a flow line here. So, similarly, these are equipotential, this is equipotential line, these are all equipotential line, these are equipotential line, equipotential line, equipotential line, and this is also equipotential line, this is also equipotential line. So, now this only one thing to be remembered, that flow line and equipotential line, they intersect each other at right angle. This is one thing to be remembered, and there is another guideline which I will mention in later. So, this is based on that one has to draw this, and now using this how to find out the seepage, that has to be seen. So, from here one element can be shown in a large view, and that is actually, see, this portion is suppose this portion is suppose L, and this portion is suppose B. So, L and B dimension, and from a flow line I took only one element actually, which having length L and width B, and flow is taking place this direction. So, what is the area through which flow is taking place? B times 1, suppose I take unit width. So, B times 1 through which flow is taking place. So, based on this, now I will see, I will take another thing, that is I am considering now 3 portion of blocks. One is this one by ABCD, and I am taking in the same flow line at different location A1, B1, C1 and D1 suppose. So, with respect to this, what is the relationship? Both the blocks in the same flow line, and similarly I will take another one here. With respect to this, what is the relationship here? They are within the same equipotential line. So, these two this is equipotential line, this is equipotential line. So, this block is there between two equipotential line. Similarly, this block also it is there between the same equipotential line. So, if I do this, compare with this and this, and comparing with this and this, we will be able to reach some conclusion, and that conclusion helps us to derive the flow quantity. So, I will proceed to this. Now, you can see the figure whatever shows a typical flow net representing seepage through a soil beneath a dam. The flow is assumed to be 2 dimensional. Oh, sorry. And then from the Dutch's law, Q equal to AKI, and since it is small unit, then I can write in each flow net flow channel it is del Q. So, del Q equal to K times B into 1 actually is the through which it is passing, and I is the I. So, B if it is take a 1, so it will become K B into I. Now, in figure ABCD is bounded by, as I have mentioned, ABCD is bounded by the same flow line A1 B1 C1 D1, and again by the same equipotential as in ABCD. So, this is with ABCD I will relate this one, with ABC I will relate this one. So, if I relate this one for any figure in the net, del q equal to K del H into B by L, and del H actually head loss between the two equipotential, and L is the distance between the equipotential. If I consider this, then you can see flow through A1 B1 C1 D1, it will be del Q1 will be K times del H1 B1 by L1, and flow through A2 B2 C2 del Q2 if I consider, then K del H2 B2 by L2, and flow through ABCD, which I can say del Q K del H B by L. Now, I can draw the flow net in such a way L1 will be equal to B1, L2 by B equal to B2, L by B. That means, what I have to do? I have to make the net in such a way that all blocks will be approximately square. They may not be of equal size, but each block if you look at, then it will look like a square only, approximate square. When you do that, then it will be B1 by L1, B2 by L2, B by L equal to 1, and if that happens, then square ABCD has the same flow lines as ABCD. So, del Q must be equal to del Q1, and since the square ABCD has the same equipotential as ABCD, then del H also will be equal to del H2. That is another condition. So, this gives you del Q2 equal to K del H2 equal to K delta H equal to again del Q equal to again del Q1. Whatever we have derived del Q equal to del 1, and this is since equal del K delta H equal to delta H and delta H2. So, the delta H2 I can substitute by K into delta H, and K into delta H is nothing but del Q from here, and that del Q also equal to del Q1. So, if that happens, so del Q equal to del Q1 equal to del Q2, and del H equal to del H1 equal to del H2. So, if I make the flow net with a square shape, then this happens that each drops will be delta H, and each channel the flow will be flow quantity constant, which will be equal to delta Q. And if I consider that, then it will be everything will be simplified. Then assume H total head and Q is the total quantity of flow, then our delta H will be total head by number of drops, and del Q will be Q by number of flow channels. The ADF is the number of flow channels, and NE is the number of flow drops. So, del Q will be H delta H B by L. So, K times delta H, and again K into H by N D. So, this will be K times H by N D equal to Q by N F. Q by N F is the delta F, and K times del H by N D. So, this one delta H is I can substitute by H by N D. So, K times del H by N D, K times H by N D, and again del Q equal to Q by N F, this to be equated. If I equate that, that gives you Q equal to K times H into N F by L D, where is K is the coefficient of permeability, H is the head loss from upstream to downstream, it is number of flow channel already I have, and this is number of drops, number of equipotential drops, head equipotential drop. So, that means, if I draw the flow net, from there I can approximately find out how many flow channels, and then I can count how many equipotential line I have drawn, and based on that I can imagine how many potential drops. So, N F and N D will be coming from the figure, and H also will be coming from the difference between the upstream and downstream head, and K is the known property for the soil. So, if I know that, then I can find out the quantity of slippage. I think I can close here. I can rest of the things I can do in the next slide and maybe next lecture. Okay, thank you.